All right. So, Ellie introduced it already, but about a year ago, StarkWare asked us to build a Stark-friendly hash function, or to analyze hash functions which are efficient for their system. So, we had a look at SHA-2, SHA-3, we had a look at the block cipher AES, and well, we concluded that they're all shit. Now, don't get me wrong, they're very secure and they're very good for software and hardware, but they're not optimal for Stark systems. So we answered back to StarkWare and we said, we can do better. Let's make our own ciphers. And well, we said, okay, StarkWare. StarkWare, this name, this seems familiar. So we thought, okay, we have a good name, we have a good application, we're good to go. And actually with that, I'm gonna take off these sunglasses because I can't see anything. Good. So there are differences in metrics. I'm gonna go over them very quickly, of course, between the classic model and the Stark model. So in the classic model, think of software. Everything works over bits. Your computer invariably works over bits, so your symmetric key primitives, they should work over vector spaces of F2. Better yet, those primitives, they should respect the platform's architecture. If you're working with 32-bit microcontrollers, your primitives should use 32-bit words. We know that it's better to work with small S boxes, because with small S boxes we have search methods to see which S boxes are efficient, low in XOR costs, low in AND costs, and we can also have brute force methods to see their cryptanalytic properties. Same reason, it's better to work with light linear layers. It's better to work with linear layers which have low XOR costs, as these linear layers can be quite costly in software. In a Stark model, you'll see that everything is completely opposite. Yes, Starks work over bits, or binary extension fields, but they can also work over prime fields. Everything efficiency related over Starks has to do with the multivariate polynomial description that describes the symmetric key primitive. You want that this description is of low degree, and that there are only few of those polynomials that describe it. As a result, it's better to use large nonlinear layers, large S boxes. Because if I use the function x cube over f2 to the 9, or I use it over f2 to the, let's say, 1025, the cost is roughly the same. It's one polynomial of degree 3, but of course the cryptanalytic property is just increased. The same reason, linear layers, they don't add a multivariate equation. They don't add to the degree of a multivariate equation, so they're basically for free. It's better to use heavy linear layers, a state-wise MDS matrix, for example, instead of light ones. And so we started. And this was how we got to our little butler, Jarvis. And we started with AES, and AES 128 has, every 10 rounds, and every round has 16 inversion functions there, each working over a byte. Now we thought, why not change those 16 inversion functions by one big state-wise inversion? We went from 16 multivariate equations to 1, so the efficiency just went up 16 times, and the cryptanalytic properties increased, so security increased. So we're doing something good here, right? Better yet, because you're now working with a nonlinear state-wise operation, just remove mixed columns and shift rows. They're not needed anymore. Now for the linear layer, what we did, for the affine layer, sorry, is we used the state-wise affine layer, which is a composition of 2, such that the composition between them is of full degree, but the 2 parts, they are of low degree and thus Stark friendly. Now, this is innocent little Jarvis, and well, innocent little Jarvis got attacked. And the reason why is because, well, yes, I said the design metrics are completely different, but also the attack vectors are different. And so Jarvis was actually attacked with the Grovner base attack, an attack that, well, has been used against classic symmetric ciphers, but they don't work very well. what Grovner-based attacks really do is they also use a multivariate polynomial description of the primitive. A description very much alike the Stark description or the algebraic intermediate representation. And so what happens is that while this description is very simple, you can represent the inversion function as 1 over x, which is a degree 1 rational function. And you can again decompose your affine layer into low degree parts. As a result, poor Jarvis got ruthlessly attacked. Now, we didn't stand for that. We rebuilt Jarvis, made Jarvis stronger, made sure that he was capable of fending off this Grovner-based attack. And the result is Vision. And Vision is a block cipher, and it's a good moment to say, okay, but by fixing the key, something went wrong with the slides there, but good. So by fixing the key, it becomes a permutation, and you can use it in sponge-based constructions. So you can also use it to make it into a hash function or authenticating data. And Vision has very interesting properties. Properties that Jarvis, for example, also didn't have. The first is that it's resizable or flexible. Because you can change the security size or the key size to what you want. You can also make Vision work over arbitrary finite fields as long as that finite field is a binary field. Also, you can choose the number of state elements Vision is working over at will. As a function of that, we can determine the number of rounds that Vision needs to be secure. Vision consists of 3 main building blocks. The first is M, and this is the linear layer. This is a state-wise MDS matrix, so it's very heavy, but of course in efficiency you don't see it. The second is an affine layer, same as Jarvis, which is of low degree, such that it is Stark friendly. But we mix in the compositional inverse of this affine layer. And the reason why is such that the relation between the inputs and the outputs of Vision are always of high degree and dense polynomial representation. And it's because of this trick that Vision will prove to be the most efficient in its domain. The last block is to again use inversion functions, and with inversion functions we stop differential and linear attacks. So this is Vision, our android, working over bits or binary fields. We have a second design, Rescue, our secretary, who in her free time fights crime. And the algorithm works over arbitrary prime fields. So this is now prime fields, no more binary fields. And the design is very elegant. It consists of 2 main operations. The first is a linear layer, M, which is the same. And the second is a power map, x to the power alpha, where alpha is taken as small as possible for the application. Now we consider 2 main attacks. The first is a Grovner-based attack. I said this before. The Grovner-based representation is similar to the representation that Stark used, this algebraic intermediate representation. So this is invariably an attack. The second is an interpolation attack. An interpolation attack is very dangerous because it's way more efficient than a Grovner-based attack. So you want to stop this attack as quickly as possible. So this is the reason why we mix in the compositional inverse of our power map x to the alpha, which is x to the 1 over alpha, which is a power map of very high degree, but still in multivariate polynomial form is a degree alpha equation. So it's very Stark friendly. But what this does, so how an interpolation attack really works, is that it starts to take the input and output of Rescue, starts to make a polynomial equation, and if this polynomial equation is of low degree, or is sparse, then you can attack the primitive. Only 3 rounds of Rescue are needed to stop and kill off the interpolation attack. So it's evident that our designs are awesome, but I'll spend a slide to them anyway. Now I said before that the designs are very flexible. You can choose the number of state elements that are in the design. Effectively what this does in the sponge-based construction is that you can choose what is your rate and your capacity. And by increasing your rate, what you can do is with one sponge call, process multiple inputs or multiple messages at once. This is useful, for example, for Merkle tree applications. Now, why is this very interesting is because we've shown that the more state elements you have, the number of rounds you need for vision or rescue to be secure actually lowers. That means that processing multiple elements or messages at once actually has a positive efficiency trade-off. A second interesting property is that, well, if the application allows for it, you can change the size of the base fields the primitives are working over. By increasing the size of the base field, the rate and the capacity in the sponge again increase, so the security increase, and you can process more elements at once. But the efficiency of the designs, they remain the same. So basically, you have a very, very good trade-off here. So last but not least, I said to you before, we use this inversion trick to kill off the interpolation attack quickly. Because of this, like, our designs are the most efficient in its domain. And with that, I wanted to thank, wrong company, StarkWare, for all the collaboration this year. Thank you.
We have time for 2 questions, but we don't have questions to match them, so thank you, Siemen.
Thank you.